Hey, Danny, are you on?
He's muted.
Danny, you mute.
Oh, there he is.
Okay. All
Yeah,
right.
because I need to use my iPad to join the meeting at the same time because I don't have a camera and also the microphone in this class.
It's okay. You don't need to turn on the camera.
Okay.
Yeah. Okay. Okay. Look, you can start. Yeah.
Okay. I guess I'll go over 3 things today. The code I made for the thermocouple to work with the DAC. The code for the CMOS acquisition to work with MATLAB. And then lastly, we'll also look at the MATLAB reconstruction code and NIRFAST. Okay.
Hey, it seems there's an echo.
There is an echo. I agree.
Danny, I think did you use two devices?
Yeah.
Can you turn one off? Yeah. Turn one off. Yeah.
Yeah. Because
Hey, Kenny, just mute until you need to say something.
Okay, yeah, I just turn on my iPad because I just supposed to say something, yeah. So I turn off my iPad.
Okay.
Okay. Are we good?
Look, you want to probably use the full screen. Now it becomes smaller of your screen.
I know. Again, I was just showing all of what I'm going to talk about today. Okay. Sound good?
Yep.
Okay. So can y'all see this okay?
Yes.
Okay. So I haven't given you these folders. They're on the no, actually I did give you this data. Which is under thermocouple monitor and CMOS operation. So first I'll talk about the thermocouple, and y'all can rewrite it. This was written quickly to take temperature data for the heater tests. I wrote this while I was in LBO2. So there's something you can do to optimize it, I'm sure. So the main script you want to use is called testing conversion. And let me double check. Yep. The main script you want to use is testing conversion. And
look, sorry to interrupt. In terms of control the heater and reading the thermocouple from the MFT system, is that already is separate from this code, or is it basically the same thing?
It's separate. So I can go over that, but that's just me teaching you what a PID is. It's not really like I haven't written anything for that because you don't write anything for it. It's just it's a package solution.
So I'm saying, like, for example, if I want to, so currently in the MFT, when we turn on the heater, we just turn on the switch. Is that correct?
Yeah, and it all works.
So it's not like any made-up coding or anything like that. Okay.
All the processing is done with the controller.
Okay.
Is that so all this is if you want to have temperature data saved to a computer, right? So it's much easier. I don't know what y'all were doing before to record temperature as a function of time, but it's much easier to just turn on a computer and let it run and walk away instead of standing and waiting every 5 minutes and recording what a temperature dial says, right?
So this one is mainly just reading the thermocouple data, but for turn on the heater, we just turn the switch on.
Yes. So this is just, it's something that y'all might use in the future. Again, it's easier to let the computer take the data for you than it is to try and wait every 10 seconds to write down a number, right? And this will do it at higher accuracy at a faster rate, and you don't have to, it's not as susceptible to human error during recording. Again, you can take this, you can write your own. I really don't care. So again, it's not as polished as everything else because, again, it's not an integrated system. It was something I wrote in LBO2 so that we could take the data and then I can save it. That's all this does. But the idea is, so a thermocouple basically produces a small voltage as a function of temperature. All the DAC does is read that voltage and record it. Okay? So what you have to do as a person is you have to calibrate the thermocouple. The thermocouples change, which is voltage per degree Celsius, is very well known for each type of thermocouple. However, the y-intercept is not. So basically, you just have to measure the y-intercept, which is a very simple procedure. You get a glass of ice water, put the thermocouple in, let it sit until it's stabilized, and then record what the voltage is. So then you have your first, so you have what the voltage of the thermocouple is at around 0 degrees Celsius. And then what you do is, it's pretty easy right here. Use, again, point slope intercept form. You have your V naught, which is the voltage of the thermocouple at around 0 degrees Celsius. Again, it's not always at 0 degrees Celsius. Here I measured it actually at 7 degrees Celsius. But you may want to double check all of those. But the slope is pretty well known, which is the M. And for here, the K-type resolution is 41 microvolts per degree Celsius. So this first paragraph here is just setting variables. Temp is basically, I use this as C naught, which is what the temperature of the ice water is. Basically, you just need 1 point to calibrate the system, calibrate the thermocouple, as long as you're not going too high or too low. F name, it's just, what do you want to call this? Because I have, after it records all the data, it sends it out as a CSV. You can change the name of it. Obviously, you want to keep CSV. Total time, sorry, it's actually total time. You can see it's 60 by 45. And I can, so my computer's frozen, if you'll give it a second. But what I did there is basically, come on. All right, give me a second. Sorry, guys. Sorry, I'm trying to see if I can find it on my computer. And we can just do that. Okay, I'm gonna pull it up on my personal computer since we're not doing it. Sorry for the wait.
Hey, look, I just wonder, because when we record the folder name actually is different than what it show on the local transition folder. I wonder if you can just rename it as a same name, same folder name. Because when we come back, we're going to look at this record. We know actually which one is which, you know.
So I haven't given you any folder names for these files. So there is no folder name for it, right? You can just
it's just the
folder wherever you want.
No. I'm saying like when we first record, actually we record that one is in the. Actually, that's fine. You can use it. It's okay. Yeah, I guess it's fine. Yeah.
Well, again, when we first recorded yesterday, actually that is the correct file names, right? It's all going to be here.
Yeah.
So that is correct.
Right. But what I'm saying is like, for example, you record a thermocouple monitor, but in your transition folder, it is not named as thermocouple monitor. You know.
Oh yeah,
like
testing. Yeah, I can change. Yeah. I'll just change the name to thermocouple monitor.
Yeah.
Okay. Yeah, that's fine. I'll just. Monitor. Transition. Okay. Let me double check. Change something earlier. I want to make sure this change still holds. There it is. Okay. So to pick up where I started, total time is again is total time or total time of experiment in seconds. So you can tell last experiment was 45 minutes. So total time is time that data is averaged over. RES resolution is basically how fast the data will be taken. So the resolution is 0.1, so it's ACQ acquisition time in seconds for DAC. So that's basically every 0.1 seconds a data point is taken, and then after 5 seconds all the data is then averaged. And then here is the number of averages per second. There's too many of these. You can go back and cut most of this stuff out. But that's how I wrote it. So here, this is temp V naught. So this is a variable. That's the voltage at the set temperature. So this is a measured value. So voltage measured during calibration at C naught. Again, this is the temperature set up here. For here, I have it as 7. You may want to double check. Temp.m is, again, that's the slope. So basically, it is the thermocouple resolution. Next one, this is to initialize the DAC. And the input is just an integer, which is how many, number of temps, so number of thermocouples starting from analog input 2, because analog input 0 and 1 are taken by the Galvo system. So the really important part here is that after it's created, you have a number, you have the channels initialized. So if I have to go from initialize AI2 and then AI3, and what this does is it changes the configuration to single-ended, and the really important part is it changes the range. So typically, if you just turn on the DAC and initialize a channel, the range is going to be from negative 10 volts to 10 volts. But understand that the resolution is, I believe it's 16-bit. So, it's 16-bit over 20 volts. You're not going to see any thermocouple measurements. You have to change it to the smallest range, which is, this is negative 0.2 volts. So negative 200 millivolts to positive 200 millivolts. So a total range of 400 millivolts. And then you have a 16-bit resolution to be able to see the thermocouple measurements. So that's really what's important here. So this is just to initialize the array, so to actually save the data. Basically, it's just a for loop. That's all it is you take a for loop whose length is basically the total time divided by the time that you average. Pretty simple. You measure the temperature. All this does is tell you how long you need to average over, what our resolution needs to be, how many samples you want to average over each second, and then your object, which is the DAC. It takes the measurement, reshapes the data, and then sends it back out. So once it's sent back out, you have the data here. We take the mean, standard deviation. I also take the error just to take it. And then from there, we convert it. So you take the data, you do, again, it's just a point slope equation, linear equation, then convert voltage to temperature. Actually, I'll just put this here. Point slope formula to convert temperature to, voltage to temperature. Next, I do have it basically, this only works for 1 and 2. Here you could replace all this with a for loop, but I had 2 thermocouples. So this just spits out number 1 and number 2 information. It just spits it out to the command window so you can see it, and then also tells you how long, how much time has elapsed, and then from there it adds to a graph so that as time moves on, the temperature changes, but then you can see how the temperature changes while you're making your experiment. Then once it's done, records how long it had taken, and then writes all the information like the temperature, the interval time, so how much time it was averaged over, and then the date, and writes that to a matrix, writes that to a table that's then saved as a CSV that you can pull up in Excel. Any questions? Hello?
Yeah, it's good.
Yeah, okay. So it's pretty simple, but I found it useful. You may not. Okay, so the next one is, just delete all these. The CMOS, and for this is in the equipment scripts, CMOS. I only wrote 2 functions for this, so you can change it around if you want. I have a testing camera .m script. This is just a script to figure out how to get it to work. So it's a little much, because basically what you're doing is you have a .NET assembly and you're adding that assembly to MATLAB. And I don't know if y'all have ever tried using .NET assemblies in MATLAB. It's a little finicky sometimes, but when it works, it works. But basically, that's what you're doing. That's what you're doing here. Is so you want to make sure that the actual IDS, so the software package that I've put in there for that CMOS camera, it typically, the DLL does save there. If you install it and just let it do its regular thing, this is the path for the .NET assembly. If you change it, then obviously you need to change this path to wherever this UI.net.dll is, so the DLL assembly, because that's the important part. Without this, it won't work. Then from there, you create the object. This is just an error. Basically, you shouldn't have more than 1 camera in there, so it shouldn't matter, because it will just, it's going to open the first camera. If it doesn't do it correctly, it says could not initialize camera. I suggest unplugging the camera, plugging it back in. That computer only has a couple of USB ports that work correctly. You need to make sure that it is USB 3.1 with that camera in order for this to work properly. So basically just unplug it and plug it back in until it works. That's what I did. Or, sorry, unplug it, plug it into a different USB port until it works, because there's a couple on there that aren't USB 3.1. This just sets a lot of this is basically just setting up the camera. I suggest not messing with it. You can probably change the color mode from 8-bit RAW to something else. Again, you do need to remember this camera, I think, is like 2096 by like over 3000 pixels. So if you're saving images in RAW 8-bit, it takes up a lot of information. It's a pretty big file. Just keep that in mind. And then the rest is just, it's pretty self-explanatory. What it does, it's just setting up everything. The important thing is the acquire image, extract image, and then draw it. This is the important stuff right here, which if I take you to the other 2 functions, this is how it works. Is basically you have an initialized camera. You just, in any script, you write this, it'll spit back cam, ASM, and image, which is basically, the idea is that cam's your object that you're gonna control. ASM is actually the assembly object, so you have to have that there so it can access it. And then IMG, if you look down here, I think it just basically tells you how much image memory you can have, but also what's the width and the height and the bits. Basically, it's all the information you need to make the image correctly. From that, you can use these objects, image, cam, ASM, to then take pictures and then have it send the data back. And basically the image data, it sends back a matrix, but it's called image.data. So it's in this structure. You just pass the structure back across. Does that make sense? Hello?
Yeah, look, it's good.
Okay. So that's basically it. It works pretty well. be careful to, if you initialize the camera, and this is kind of important, you need to make sure that you do cam.exit before you close it down, or before you clear the variables, because if you clear the cam object before you do cam.exit, you can't access the camera anymore, so you'll have to turn it off and you'll have to unplug the camera and plug it back in. That's the only issue. There.
So look,
yeah.
Can you make a comments here? I think
yeah.
it's okay. Yeah. Okay. Because there's that's an error. I think it's okay. Yeah.
What error?
Oh, I think Jack just asking, can you provide a little bit more detail as comments, like just what you talk about the closed camera?
Oh, yeah. Let me do it in initialize camera. I'll put it kind of up here.
Yeah.
It's an easy fix, but it's something that can happen by accident. Which is you know, when you're done, you type into the command window clear all, and if you haven't exited the camera properly, it messes with it. So basically, where the issue becomes is if you look here, is when you go and try, because you can also just use this software. I don't know if I got to show it to any of you. I think I can open it without, yeah. So you can also use this to just, if you need to take a picture quickly, you can take the picture and then save the picture. You can you take videos here as well.
Okay.
But if you clear, after you've initialized the cam object and you clear all the variables before doing cam.exit, even this software won't recognize it until you unplug it and plug it back in.
Okay.
So that's just to help you with that. Like I said, when using .NET assemblies in MATLAB, it's a little finicky, but when you get it working, it's fine. Okay, so that's all of that. Okay, so the next thing, do you have any questions?
Hey, look, I think next one we are going to do the talk about reconstruction, right?
Yeah.
Hey,
yeah.
So I wonder before that, do you have any list showing like, for example, which software is for which hardware? Like in this, actually the one you show me, the camera actually is my first time to know. Oh, that's the software for that camera.
So you want to list? Well, to be fair, that CMOS camera isn't a part of anything. I mean, if you know the name of the company, it's pretty easy, right? You know, Zaber is for, well, Zaber's for the rotary stage because the company is Zaber. Andor is, well, that's probably for the CCD. UI, again, the CMOS is called a UI. This is for the filter wheel. I don't know if I have the, I can make a list, but you know, really the only thing that it's going to have is this is for the CMOS, and this is for the rotary stage.
How about the Platon?
The what?
The Platon. The one you have on the desktop, the Platon.
I have no idea what that is. Let's click it. Oh yeah. So actually, I was wrong. My mistake. This is for the Omega software.
Right.
Which
yeah.
I can't show you all that. I was going to show you all of that when I got there.
Right.
Which we can just like open up meetings and I can still record.
Okay.
But I mean, I can make, again, that's 3. List of software for hardware. Yeah, I think I can just make like it's only going to be 3 or 4 things, but yeah, I can do it.
Yeah, just make our life easier. Yeah.
Yeah, that's fine.
Hi, Luke. Regarding to Ken's question, I also want to ask, when we install this software, do we need to follow an order? Basically, which one we should install first, then?
It shouldn't. No,
Okay.
it shouldn't be an issue. Again, the only thing that you might have issue with, which I tried to write in the README, is again for the Zaber and the NI. And actually, the NI acquisition software support for MATLAB, it should be already on MATLAB when you download it, and as long as you choose the like instrument control package, it should come with it. So you should already have that add-on. But if you don't, which I didn't on my computer, I did put in the README, that you come to Home, you go to Add-on, drop-down menu, Hardware Support Packages, and then, okay, now it doesn't want to open as fast. Come on. And then you would just type, like NI DAQ. Oh, come on. What? That's... Yeah, I don't know why it's doing that. Yeah, so here it is. So you have Zaber. Again, you would probably just download this one. But I also gave you the download. So actually, I was able to save the download. So that's in the installs for the Zaber. And then the NI DAQ. It's right here. You can download that one.
So look for this add-on Explorer. Is that like a special module from MATLAB, or is it like a standard once we install MATLAB, we should have this?
Well, it's like a little. Some of it's extra. Again, like I said, the NI DAC should come automatically. If it doesn't, you use this. The Zaber does not. So, but luckily you have the add-on Explorer. It just does everything for you.
Yeah, but I'm just saying the add-on Explorer is a standard package from the MATLAB. That function. Yeah.
Yeah. This is all of this is it's to help with, you can get add-ons, you can manage your add-ons. Yeah, it comes with MATLAB.
Okay.
Just to help. And there's other stuff on here too if y'all are interested, like the MATLAB support package for USB webcams. So then you can control your webcam with MATLAB. It's pretty cool. I use that sometimes. And actually you don't even have to for the DAC. If you don't have the DAC, it's actually the first page. So it's right here. You can see how I've installed it on my computer. So that just kind of, it shows you how to do that. I also wrote it in the README, and now you'll have this recorded showing how to do it. But those are the only 2 things that should be like different. But everything else, has like an exe that you can just, you run it, and then you just click next until software is installed.
Okay.
Thanks.
Okay. No, this is my computer. Come on. Here we go. This is the pre-construction. So let me go through. This isn't going to be exactly the same. I've cleaned up a lot of the information for y'all. So it's a lot cleaner. But for me, I like working from mine. is, I've just called it FT code, mFT version. But inside this, it's the same. So you'll notice that everything is basically exactly the same as the QBLT, down to the fact that I didn't even rename the function. I just kept the same name, because I didn't feel like it was needed until everything's finalized. So if you open this up, everything's here. The main script you want to follow is QBLTv2, is what I've called it. You can change the name. This name's not really going to affect anything. But everything is basically taken from the QBLT. I've just modded it.
Hey, look, can you enlarge your screen, man?
Yeah, I'll do that. Sorry. Is this okay?
Yes.
Okay. Everything's the same. I just kind of changed it around, right? So input filter wavelength, I have it as technically that's like the emission filter wavelength. I added the excitation wavelength. Projection angle's the same. I kept the optical system the same because there wasn't too many differences between them. Calibration angle I did change. So to go from -60, -30, 0, 30, 60. So everything's changed as far as when you go into deeper into the functions. That's changed so that it corresponds with these angles. The big thing that was changed after that is this. I've kind of done this a couple of different ways. You can mess with it too. Is the first way, which is right here. I have the source number as an array. So basically, it's an array of, okay, 1, 2, 3, 4. In this case, it's 1 to 9. And I find that just helps when you're plotting the data. Sorry, when you're organizing the data later for NIRFAST. The other way I was able to do it was this, which is because when I take the data, it's indexed as S1, S2, S3, S4, S5, and so on, where S is called source. So I say like, okay, source 1, which is source position 1, source position 2. So this, when it pulls in that name, it saves that S as, oh, this is S1. So this corresponds to source position 1. However, I thought that, hey, what if I don't want to use 1? What if I want to use 2, 4, 5, 6, and 8? Which basically I just do that here. Is if you don't want to use like a 1 to 4, a 1 to 5, if you want to say, oh, I want 1, 3, 7, and 9, right? I kind of just, okay, you can just make that into an array. And currently I don't have, as far as I can tell in all the literature, you're not going to have like an N of 30. It's going to be, you know, at most 10 or 15, which 15 I think is even too large as far as number of source positions. But other stuff can be thought of. Everything after that is pretty much the same. You know, all of this is going to be the same as QBLT, so I'm not even going to go over it. This is going to be the same as the QBLT. What you'll notice, though, is a lot of your functions I changed, and when I changed them, I called it FT. So when you go through it, you can find all the FT. And then on top of that, I've also added, because I didn't get around to changing the function and then changing the TXT file you have for the optical properties. So I just added more, which is basically you have the absorption of the fluorophore. Absorption of the fluorophore. You have the efficiency of the fluorophore, the quantum yield, and then you have tau. So Because we're not doing amplitude modulated FT, tau is 0 always, but it needs that information. So you have 0. That's pretty simple though. But that is going to be fluorophore dependent. So this is the fluorophore properties are added here, which they're commented in. This cone beam CT stuff is the same as yours. Where this thing changes, so the big change here, as far as loading the projection data, is you use, and it's been a little while since I thought about it, but basically you use a dimension to keep track of angle. I changed it to keep track of the source position. So that was one of the next steps, is then, okay, now I have to go back, and probably what I was going to do is just cut all the stuff I've done, go back to what y'all had done, and then just add another dimension to keep track of source position after the angle position of the actual image was saved in that dimension. I haven't really thought of a way to do it yet, but that's that can be done here. As far as the time factor, I don't really have to worry about that as much. So I just I made them all 1, because you divide by everything later on down. So, divide by 1 still 1. The next one is the actual mesh generation. Here, it actually shouldn't have been changed too much. It's changed a little bit. I don't remember off the top of my head what exactly I've changed. I think most of it came down to, it wouldn't be much as far as what I've changed. It would have been basically how you call the NIRFAST and how it's saving. There's like a small difference, if I remember correctly, but it's all there. The geometry calibration auto, I didn't change any of that other than changing the calibration angles. I think it's kind of hard coded in there as -90, -45, 0, 45, and 90. I changed it to -60, -30, 0, 30, and 60. Then after that, you have getting the actual detector position. Again, the big change here is the fact that that same dimension that you were using to measure, to keep track of the angle, I didn't say, well, actually, that's the source position. So I did a couple of changes there, which all, it should all be tabulated out. And then here's actually the bigger part, which I talked about a little bit yesterday. So I came up with a couple of different ways. You can see this is commented out on keeping track of the source position, but I found this was the easiest way, which is because we've recorded during taking the data, we record all the pixel positions, which they're indexed. So basically this is a n by 2 array where n is the number of source positions. So, it's much easier to then just copy and paste that matrix into this, which is then used, again here, I just put an error, which is basically saying that, hey, this array of your number of source, your source positions, it needs to be the same size as the rows and the pixel. If not, there's something wrong. That's just because I kept forgetting to change this. The next is actually getting the source position. So kind of like what we talked about last time is, way up here, if I remember correctly, way up here you've already calibrated everything with your calibration process. So this just takes all of that information, then takes these 2D coordinate positions and then pushes back cone beam CT coordinate positions. So the return of this is basically, it's the same. It's an n by 2 array. Sorry, it's an n by 3 array at this point. It's an n by 3 array that is in cone beam CT coordinates for the source positions. That's then saved to the mesh structure. And then from that, there's a link file. Basically, you have to link each detector to a source position. That's what this does. And then from there, it saves all the data to the NIRFAST format. This is all kept here, but all of it I really needed to I need to tabulate it out. But basically, it gets to here. After this is done, it cuts off anyway. This pulls an error because I don't have all the information. So that was my stopping point. So I can go ahead and start something. It does take a minute. Is everybody okay with that?
Hey, Lucas, I wonder, like, what's the reason you pick negative 60 instead of the 45 jack use? Yeah.
What is the reason I picked negative 60? You mean, why did I do negative 60, negative 30, 0, 30, and 60?
Yeah, I saw the jack. What's the angle jack use? Like, is there any reason to change it? Or?
So if you remember correctly, all of this is based on the benchtop setup. Mm-hmm. So that's really when I changed a lot of the functions was for the benchtop setup. Mm-hmm. And with the benchtop setup, I couldn't do 90 degrees because of just how the white light, where it was set. I didn't have a uniform white light on the benchtop. Everybody's solution, they said, hey, all you have to do is just change these numbers, right? Negative 60, negative 30, 0, 30, and 60. Yeah.
So for the mFT, actually, there's no, I mean, there's no need to, we can just keep it the same angle as we use in Miracle, right? For mFT.
There's no reason for mFT, but also, you know, one thing I do want to make clear is that this calibration angle data, you change it here, it doesn't mean anything, because if you dig deep, it's hard coded.
Yeah, so that's I'm saying, like, actually I don't think it should be hard coded.
I agree, but I didn't code it. I'm not the one.
I'm not saying you coded it. I'm just saying, like, hey, Jacob, what's the reason we hard coded in the code for those calibration angles?
And I'll try and find it, but it's really deep in there. Just give me a second. Let's see if I can find it.
I think for this one, is in the beginning we use dual use. For dual use, we have to do the hard coding. I think for Miracle, we
current the QBLT code, I want to make sure it's not hard coded. I think I always emphasize it.
Yeah, see, it's right here.
Jack?
I don't. I think, but this part is.
I just went through and just changed everything and switched it all around.
Because I want to make sure it's not hard.
But I think there's somewhere else where it's.
I think this part is done by Danny.
Yeah, see, and then here's the other one is because you call it fid.03. Right. I changed all this.
Yeah, actually, I have to turn on the my radio, because actually, because you use the dual use as a pattern, as an input pattern. So here what we call is the dual use part, because actually for dual system, the angle is always fixed as the minus 90, minus 60, 45, and 0. Just 45 and 90, this space. So we don't, because that even once you use the dual use input, which means you change the angle is no use at all, because all the data we fix in these 5 angles. This is hard.
I understand, but I'm saying, like, for the currently in the latest QBLT code, is that hard coded for Miracle?
For Miracle, it's not hard coded. For Miracle, it's based on the angle.
Looks like it's hard coded though, right? I mean, this. right? I mean, this is fixed find markers, unless y'all change. Y'all probably changed it since I.
Yeah,
guess this is.
this one actually because here I use the fixed because we use the fixed searching for the method. We use fixed searching, so that's why I have to fix. Because at previously I want to use the general searching and finally it's not work well because the mouse back reflectance is too strong. So I have to fix the angle to search in the mirror go. We have to fix at the 6 angles, just minus 60, minus 30, 0, 30, 60, 180.
So okay, I understand. So it's for example, if we pick any 5 angles, that will fall into your searching your basic angle selection, right? But we cannot use, for example, minus 20, right?
In the code actually, if I release the auto searching, it works. But actually, you may not find the BB because the general searching cannot find the BB, which means there's no backup option to search for the minus 20.
Yeah, I understand. I'm just saying like, so I think in the QBLD code in the beginning, we need to have a comment saying, so we recommend to use those angles, but the other angles, like something you can also select, but that can, so basically you are saying if we keep all those angles, we have a basically higher probability to find all those BBs.
So you mean high probability.
So for example, if I just randomly put like a minus 20, but if all the auto finding does not work, then we won't be able to find you won't be able to use the fixed BB location to find BB, right?
Yeah, currently, yeah. As long as if we set up the files, just like set up the fixed BB location for the minus 20, yeah, still be okay.
Yeah, so I think in the beginning, I just thinking the QBLT code, we want to make a comment to make it clear, So so it's not really like a hard coding. It's more like it's one of the options.
Yeah, it's a function limited. So currently we have no idea because the mouse back reflector is too strong. So we cannot use the very general searching for the every angle.
Yeah, I just think like we need to have a good comment when you inside the QBLT code.
Yeah. Okay. Yeah.
Okay. Mm-hmm. All right, Luke, you can continue.
Okay. Okay. So that's pretty much all of it. I mean, it's kind of hand wavy, but it's all there. All the information's there. You just have to dig in.
Yeah, I want to ask you, in terms of all the sub functions, is there any like important point you want to talk about it?
No, the important point again was, which somebody else will have an issue with, and I kind of already covered it, is the dimension that was originally used to keep track of angle. Mm-hmm. I then used to keep track of source position. Right, source 1, source 2, source 3, 4, 5, and so on. So as soon as you want to do multiple angles, you're going to then have to go back and say, okay, because there's two thoughts, is either, okay, I can find another dimension to keep track of angle, or I can go back to what, Jack and Denny originally had and find a new dimension to keep track of source position, or a new way. Basically, it'll end up, you need to add another for loop somewhere, I'm sure.
Basically, look, I mean, if we want to use your code to do the multi-projection, we need to add another loop, right?
Would ultimately, I think that's what it'll come down to. But yeah, that's again, I haven't dug in and like, okay, what does that mean when I transfer data across? Will it carry correctly? There's a lot of troubleshooting done. But I think what it will come down to is you either need to have another dimension, because right now, if I remember correctly, the way I'm kind of doing it is basically you have I think they're called dictionary, right? It's an array of matrices. Is basically you have a matrix that's your image, right? And then your array is actually, it's indexed like the source position, if that makes sense.
Okay, look, we can dig out later. So
yeah, but that's the important thing is you want to have another way of doing that.
Yeah. So in terms of reconstruction, where do you start the reconstructions?
Yeah. So I was just gonna go ahead and run it. If y'all want.
Oh, how about let's take a 5 minutes break and then come back.
Okay. Just to let you know, it does take. I tried to turn down the everything, but it does take a little bit to map all the data.
Okay. And look, just another question. The example is the one you're going to run in these folders?
Yeah. It's the to be fair, it's the only good one I have.
Okay. Can we also take a look at what do you have in the examples? Yeah.
Well, again, I've only given you one example. It's the only good one with the data we have now. There's some good data with the 650, but that's older stuff.
Yeah, I'm saying like what kind of data format you have in the examples?
What do you mean data format?
Like what do you have in the example?
Like,
I think basically it's your raw data and also after data mapping.
Yeah.
What's your data format?
Data look like? How do you arrange your data?
Okay, we'll go through it. I don't think it's any different than what we've done before, but yeah, we'll go through it.
Okay, be back in 5 minutes.
Okay. Are we canceling?
You can keep it. It's fine.
Okay. Did you stop recording?
Still recording.
Yeah. Okay. No, it's still recording. Taking a break.
Look like it's a good paper.
Yeah, so I wrote a paper several years ago that did all of this. And they're trying to basically my old groups, they're trying to do the same thing, and this guy, he has it, but the software I used before is pretty much obsolete at this point. And he wanted me to take a look at this to see if I can make any sense of it. But I'll deal with that later. Sorry. It's for that's laser irradiation. Are we good?
Jake and Danny, are you guys okay?
Yeah, I'm fine.
Okay.
Is Denny? I think Denny's still gone. Do you want to wait for him, or you just want to go ahead and go?
Let's wait a little bit. I think
Okay.
it's not 5 minutes yet. Yeah.
Yeah, I'm on site. Actually,
Okay.
I hear so, but I turn off my iPad, so yeah, so I cannot use the mic.
Okay. So you're good?
Yeah.
All right. Well, again, basically, you'll notice once you've obviously what you need to do is make sure everything's in the correct path here before you open up the QBLT v2. But after that, it's basically exactly the same as the QBLT, I assume.
Look, before you run, can we just look at an example? Yeah, take a look.
What do you mean example?
Your example going to show us. I want to take a look at the data inside.
Oh, you want to take the data first? Okay. Hold on 1 second. Let me cancel. I'll hit Command C. Okay, cool. Yeah, let's go ahead and take a look. My apps. No, this is my personal computer. Hold on a second. Okay, let me see. This is Sorry, guys, I'm getting. It's like in computer inception. Hold on. Okay. Let me see what I'm taking. So we'll go to the drive, looks data. So basically, here's the data: cone beam CT and optical data. So the optical data is probably what you want because the cone beam CT data doesn't change. Again, for here, I have 0 degree or white light. So for 0 degree, I have these, which the idea is, here is all the emission data here, and then I also have the excitation data, and then at the end I kind of showed you as well, you have the parameter list, of which the first thing is the actual array of pixel locations for the source positions. Close that. But it's again it should be very similar to what y'all do with the QBLT. I changed around some of the nomenclature because you also have that excitation wavelength to consider as well. That's it. Any questions?
See, so if you go to the optical data, the folder, can you go back up? Yeah.
Go here.
Yeah. So this white light, basically, can you go in just the calibration angles?
Yeah. So that's just the white light angles.
Okay. So basically, that's all you need to run the. How about you? You still need the cone beam CT data, right?
Yeah. So the cone beam CT, I do have it here. But again, the cone beam CT is going to be. It is exactly the same as the QBLT. The only difference is basically we have to index source position. Like we need to track, source position.
I see. So the source position, you basically copy and paste into the your MATLAB code, and then later to write the nearby format.
Yes. Again, there's a pretty simple solution. You could obviously just have the source position pixel array saved as like a text file in the hardware code, and then have the software, the MATLAB code for organizing the data. Just do the same thing y'all have been doing, which is ask, hey, where's this data at, and just do it that way. Right now, I've just been copying and pasting because it's easier.
Sure. Do you have the output data format here? The output data from your reconstructions.
So if you look here, everything below here is that's a bunch of reconstructions I've done.
So what does it look like? Yeah.
So let's go. It depends on what you want. So as far as from MATLAB, we get these files, right?
Yeah.
Which are your element, link, measurement node, your PAA, param, region, source files, right? That's what you put in. These are some of the things you put in NIRFAST. This is what NIRFAST uses, which once we get there, I'll show you how to do it. Excuse me. And then once that's ran through, you make another folder called reconstruct, which this one hasn't gone all the way through, so my mistake. I gave you the one that I've already went through and double checked everything, but let me just go through here. Yeah, so this is what you get from the reconstruction, and what you use is actually the VTK file. So you'll use NIRFAST Slicer, and I have one open right now. You'll open the Conebeam CT, and you can open the actual DICOM files. That's what the background here is. Then you'll go to the models, and you can actually just kind of you can literally drag and drop the VTK file to the model. You do have to rotate the model. Again, this is all documented in the actual document that I wrote for this, and then that's how you visualize it. Is basically you put this in here. Here I can kind of open up another one. You can see this is another one I was kind of messing with some of the parameters. The idea is basically you have to make it visible. You have to make sure the slice display is visible. You have to bring down the opacity, and then scalars. You have to make sure that's visible. And you have to go to the ETA UAF or MUAF. They're the same because ETA is not really gonna affect it too much. It just changes the actual values, not the position. Any questions?
Jack and Danny, do we use the NIRFAST slicer for BLT?
No, we only use the 3D slicer.
Oh, okay, so I see. Okay.
Look, I have a question about which core you use for the reconstruction. Is still the CSCG core?
No, I don't think so.
Okay.
No. So I've been using NIRFAST.
Oh, just NIRFAST function.
I'll get to it. So after I run basically the only thing the MATLAB code is doing is just organizing the data.
Okay, I see.
That's all the MATLAB code is doing. It's just organizing it in the correct format.
Okay, so you use the NIRFAST function to do the reconstruction. Okay.
Well, it's actually it's a GUI. I'll show you again.
I know what GUI is. Yeah, I used it before. Yeah.
It's a simple GUI.
Yeah.
Which it's MATLAB. So again, if down the future people don't want to use the GUI, it can be. I'm pretty confident it can be implemented in MATLAB very easily. But yeah, for now I just use the GUI because it's easier.
Yeah, I remember as long as we have the mapping data, the NIRFAST format data, I think should be easy to use this GUI to run the reconstruction because I remember I went several times. Seems okay.
Yeah, it's pretty user friendly. Again, we're just using for fluorescence, so
yeah, okay.
Pretty simple.
Thank you.
Yeah.
Okay. So look at sorry, Danny and Jacob. I mean, we can consider NIRFAST slicer for the BLT as well.
Yeah, actually, this is the actually, I remember we talked about this. We want to use the NIRFAST slicer instead of the near field because actually the function is more powerful than the one we use now. But because currently I'm not pretty sure how we use the NIRFAST slicer to do the contouring and also
Okay.
Yeah. Okay. I remember we want to talk to this with Harming about because I remember after we use the NIRFAST to do the contouring, eventually they will come out a mesh as a result. It's not the contour, I remember. Yeah, so.
But But I think Luke just generate the mesh from the meta code and just use this one to show the results.
Yeah, this one.
Yeah, because there's also issues. Like I said, you have to do from the DICOM to I guess you'll do like a coordinate transform or something in the MATLAB, because again, you have to actually rotate the VTK information to get everything aligned correctly here. But it's only when you upload it with NIRFAST, as far as I found, because when I upload it in near view, it doesn't do that. Right, because at the beginning you actually tell it how it needs to align the data.
I remember near view cannot read the DICOM.
No, it can't, right?
Yeah.
Here, this can read the DICOM, and I think what you want to look for is the volumes and then volume rendering. So you can use volume to change the contrast of, here's my volume, and then volume rendering will actually render the volume.
Yeah.
Look, can I look at your reconstruction results data format? Because I want to make sure. I mean, what's the data format? It's RTK. Oh, it's VTK. Okay, I see that.
As far as I can tell, it's pretty standard format.
Yeah, because I think it doesn't make sense. The NIRFAST, they first introduce near view, then later use NIRFAST the slicer, and then become not compatible. You know, I'm sure we should. I mean, we should try.
There's a way. I got pretty close to doing it because I was just trying to use near slicer in the beginning. Nobody told me to use near view. I got close, but I had issues with the coordinate systems.
Okay.
It doesn't matter.
I think that's something probably can be solved. You know.
Yes.
Yeah. I think and Jack and Danny, actually, I went to the OSA workshop. They actually teach you only use the nearby slicer. I don't think. I do think we need to migrate to nearby slicer because it's just easier. Yeah.
Yeah, I agree. Yeah, the last time we go to the OSA, also they only use the slicer.
Yeah.
Of course, we can use slicer to generate the contour. I think there's no longer any problem. Yeah.
Right.
I agree. Okay.
Yeah, because actually the slicer have the same function as the 3D slicer, so yeah, I think should be fine.
Okay. All right. Thank you, Luke. You can continue. Yeah.
Okay. So let me close all this. I just pulled it up. So this reconstruction is not going to be accurate because I turned down a lot of the information. So it's only going to map 5 source positions, and then I think I have like a 16 times attenuation for the density, just so we don't want to be sitting here all day. Let me go ahead and run it. So it's the same thing. You pick the spectrum for this. I did make a spectrum file. I kept it just to keep it for the future. Obviously, the spectrum file is 1, so that when you weight the spectrum, you're just multiplying or dividing by 1. For the optical properties, those are changed. So I have mouse phantom FT test that Ken was nice enough to give me the information on the actual optical properties. So I did change it for the wavelengths stated. Cone beam CT. So select optical images. 6 data. So choose folders. So I'll go back out here. I'll call this reconstruction 13. Kin and all test. So then, obviously it's the same thing. I didn't change all the all the settings, but the first thing is to filter images at 0 degrees. 1 through 5. So 1, 2, 3, 4, 5. Open. So open the contour. That's the same.
Okay, yeah, you have 5 images just because you have 5 different source position, right?
Yeah. So I have 9 total for this data, but I changed it to 5 while y'all were talking, just so we're not sitting here all day.
Okay.
Again, that's what I tried to preface before. This reconstruction will be wrong, and then obviously, you want to do the calibration, and hopefully it works.
Did you use the NIR slicer to generate the control file?
No, I use, it's the exact same, like near view, and then, use MATLAB and then the near view. So I got close to creating an MHD file, and I actually did make an MHD file with near slicer at one point, but NIRFAST, it basically, in near view in the beginning, I don't know if you remember, but you tell it how to align all the data. Basically, you're rotated 90 degrees from near view when you just import it automatically to NIRFAST. Basically, you need to remember to do a rotation transform on the Kang-Hsin CT data when it's imported into NIRFAST, which I will show you here in a minute.
Yeah, because actually the orientation in the sub and in the optics is different, so that's why we have some translation.
Yeah. No, I completely agree. But again, NIRFAST just uploads it weird to the Kang-Hsin CT.
Yeah, I remember NIRFAST slicer is not converted to do the orientation change. It's not.
I'm sorry.
Yeah, I just mean in the NIRFAST slicer, I remember that's not easy to it's not as easy as the near field to change orientation.
No, actually, it's very easy. I can show you how to do it. It's just you have to learn how to do it, and there's not much.
Yeah, but
I had to sit there and play with it, but I'll show you how to do it. It's actually very easy to change. Change it.
Yeah, you can change. I mean, you have to manually open the head file of the.
No, not for NIRFAST slicer. No. All you have to do is you can do transforms to the data, so you just do like a rotation transform to the data, and that's all you have to do.
Can we generate a general file, just like we can use this transformation file to apply to the other mice?
Maybe. I mean, it's not hard. So right now, it's in registration. It's called transform.
Yeah, I know this.
So you can do a translation and rotation.
Yeah.
I've been doing rotation.
Yeah, but
might be able to do what you're saying.
After you do the translation, can you save this file and apply to the other mice? This is the I want to ask.
I think you can. I think you can do.
Okay.
Like, create and then save it. I think you can.
Okay.
But you may want to. Again, I would talk to Hamid about it. I'm not.
Yeah. If you can, since that we can generate just a common file, just to this file can be applied to the other mice, so we do not need to transfer for each time. So
I see what you're saying. I think you can, but ask Hamid.
Yeah, because actually this is I want to ask Hamid is, can we do just a general translation, the orientation translation? It's not like we have to do for each mice. I don't think it's convenient. So that's why
I'm sure you can save it and then just apply the transform to everything.
Okay.
And in fact, I think you can open up, like if you go to like volumes, you can open more than one mouse. So the idea is you can open up all your mice in
I
the
know.
file, create a volume.
As long as the
then,
file. Yeah, I know
and then
this
transform it, and then you can just select. Oh, I need to transform this. Okay, transform it.
But you have to input your mouse data at first. If you're not, you have to you have to put all the mouse data into this translation. This translation become a group. It's not individual. So that you can no longer just simply just copy just like the near view. You can easily copy the head file to the other mice, and we can just simply just click next and just all set. But in this, I haven't found out the function similar to by using the NIRFAST slicer.
Okay, I mean,
I think that should be a way, because actually this is not very difficult issue. So it should be a file to save the orientation.
I'm sure you can just save it and then apply it to all. Do like a batch apply. Yeah, just talk to Hamid. I'm sure he'll let you know. I didn't need to do that ever. So obviously everything's mapped. Again, like I said before, this thing will actually spit out an error before it ever gets to the reconstruction, so I kept it that way. And I'll go to the actual reconstruction 13. So this has everything in it. Before, it has your 832, all the information you need. So what I do from here is I clear all, close all. And this will be different for everybody. So, depending on where you put this file, it will. So you have to go to open the NIRFAST 9.1. For me, if I remember correctly, I've put it in the MATLAB. So NIRFAST 9.1. Just add the path, and then you type NIRFAST, and I think it's just till. Sorry, I did it wrong. So you type NIRFAST and then apostrophe after you've added this to your path, and a little GUI will pop up. Okay. So what you want to do is you go to reconstruct. Under reconstruct, you go to fluorescence. And here it'll pop up another GUI. So for input, this is the actual. I guess it's the dot node. So you go back to your reconstruction data. Oh, sorry, I'm in the wrong folder. So here, and it's in data here. Okay, here's the reconstruction we just did. Go to the mesh file. Then obviously you want to use the 832, so whatever the wavelength you're using. Open. Go here. Same thing. This is the .PAA file. There. And then you want to go, okay, where am I going to save my solution? I'll say solution 1 and all. Looks like that's Kindle. And I'll call it reconstruct. Right. Here, your reconstruction basis, as far as I can tell, I've been putting the same thing in, but this is actually where you would put like your prior information, where, and I think this is where you would put like mesh. You would make a mesh saying, okay, well, we think it's, it's here. As far as the reconstruction.
I think the other one is actually when you do the iterations, do the reconstruction. So basically in NIRFAST, you can choose two options. One is they will map your data back to the standard, for example 20 by 20 by 20 mesh. they reduce the number of the nuts during reconstruction, or you can put another set of mesh. That's the choice here.
Okay. I've been going with, you know, again, the 20 by 20 by 20. The rest doesn't matter. Well, it does matter, but, you know, obviously we're not modulating. I keep the regularization in the solver as automatic. And then basically deselect view solution, click done. And if everything's done correctly, one of the issues I had is that this thing won't say busy, but if it's done correctly, come on. All right, it won't do it. Why won't you? There we go. You'll see moving sources, source detector, creating coarse mesh. This will probably take about 20 to 30 minutes to push everything through. Any questions while we wait?
Look, actually, you can, if we did 20 to 30 minutes, you can stop. You can just use a 10 by 10 by 10. I think it'll be quicker. Yeah.
Okay.
I think it seems it's still working, or it's finished.
Y'all don't need to sit here and watch it. It's run. So let me quit. Because y'all don't need to watch it. It doesn't even matter. We don't. There's nothing crazy about it, right? I mean, do you want to watch it?
It's okay. You can skip this. Yeah. Just we can go to see. So what else after this? Yeah.
Well, after that, basically, that's when you get the. I'll do an older one. Again, a lot of these I was just kind of messing around. Actually, this one will probably be fine. So once you do it, you have your reconstruction folder. That's where you get all of this stuff. Well, actually, sorry, that's where you get all of this. So everything highlighted is what's produced from the reconstruction. The only one you really need to worry about is the VTK. I think it should be. Hold on, give me 1 second. Let me double check. Yeah. So it's the VTK file is the one you want to worry about. Yeah, here. From that, what you do, so I'll go ahead and I'll actually start NIRFAST Slicer up by itself just to show you everything. So you have NIRFAST Slicer. Okay, it's pulled up. So with NIRFAST Slicer, you can go to this DCM. So this is the DICOM. What I typically do is I delete whatever's in there because I was having issues of it pulling the wrong. Sorry, click remove. You can go to import. And what you do is so what I'm going to do is find your the DICOM, so the folder with all the DICOM files for the cone beam CT. So here, click import. It will import all the data. Just give it a second. Okay, we've imported it. You can click OK. Then you'll select on this, and you'll actually click load. So give it a second. Okay, here's our guy here. And what I typically do is I go to volumes, and I'll go down to threshold, and I'll kind of play with the, well, hold on, threshold, yeah. I kind of messed with the threshold a little bit. But it's not really needed here. That's there just to let y'all know that you can go to volume. You can kind of adjust the threshold to where you think it needs to be. Again, it's not going to do well because I'm controlling another computer. Once you have that, you can go to models. And typically there'll be nothing in models. So this is where you actually take that VTK file, you'll grab it, and I just drop it in here, and it'll say, hey, do you want to do this? And you click OK. So then you have this, it's called Reconstruction 4. So obviously we want it visible. You can see it visible in the 3D display, but we want it visible in the slice display because we didn't generate a volume with the cone beam CT. So you click that, and the first thing you'll notice right off the bat is that it is 90 degrees from the cone beam CT. From there, I usually change the opacity a little bit. I click Scalars, select Visible, go to Active Scalars, and click ETA MUAF. So this will actually give you the reconstruction, which you can then, you can see is kind of right about here. Actually, it did okay considering. So it's a color map, but we're still kind of messed up here. So what you do is you go down to this modules, you go to registration, go to transforms. From transforms, you go to active transform. You want to create a new linear transform, and then you'll have to give me a minute. It always takes me a second. Now, what I typically do, there's two ways you can go about this. Is you can either rotate the actually what I do is I usually rotate the cone beam CT. So I'll go ahead and transform it so I can see what I'm doing, because I always forget which way to rotate it, to be honest with you. I think here is 90. And then you want to rotate this 180. And then bam, there you go. So that's there. I usually like to go back to models and then kind of play with the opacity. Let me see if I can remember zoom in. I think it's control. Yep. So then I can kind of scan through here. I can change the opacity to see, oh, hey, is that okay? No, that's not very good. So maybe I want to change my contrast here. So then you can see, oh, well, actually, yeah, we're kind of off there, right? Which we've talked about this. Which the controls for 3D Slicer are going to be very similar to any other slicer. Sorry, the controls to NIRFAST Slicer will be similar to 3D Slicer, as far as I can tell. In terms of, you know, you rotate your center wheel to go through the slices. You hit Control, rotate the center wheel to zoom in and out. You hold down your left click, and you can move up and down or left and right to change the contrast of the DICOM, the contrast and the brightness. And then you can click the center wheel to translate. Okay. Any questions?
Okay, so look, is that everything?
That's pretty much it. Yeah. The rest is just, okay, you have the data, you can go through and, you know, look at the data however you want.
Okay.
If you want, you know, sometimes I also, what I'll do, just to get an idea, so if you go to this, if you go back to the mesh file, one thing just to kind of put, there is a file called source file. So you can open that up in Notepad, and what you'll have is you'll have the source position number and then the X, Y, Z coordinates and cone beam CT coordinates. So what I do sometimes also, I don't know if you remember the pictures. Is I'll go here, and I'll just create a fiducial. Then I think you can come down and actually you have to click persistent, click fiducial, and then from that you can kind of. Oh, okay. Well, my computer's frozen. Basically, you can use the fiducial. Basically, with the source positions, you know the source positions, you can then just make the fiducials where they need to be. Is kind of what I was going. That's the only other thing I can think of.
Okay.
That's it.
Look, for in your example in the transition folder, that include everything we need, right, to run the examples.
Yeah. So everything's in there. Again, if you want to run it and then view it, you're gonna have to download Slicer. But I did not. I don't think I put Slicer in the installs, NIRFAST Slicer. But you know, you need to download it.
Yeah. Can we go to the transition folder example? I just want to make sure we have everything there. Yeah.
Yeah, that's fine.
In the
pull it up on my actual computer because I'm on my actual computer. So we have this. So FT reconstruction code, MATLAB data. So you have the optical data, right? You have 0 degree, like I showed before. You have the white light data, like I showed before. And then if you go back, you have the cone beam CT, you have the MHD file, that's what you need, but you also have the DICOM files here, or DCM, however you want to call them. That's all you need.
Yeah.
Then also the actual MFT version, you have the QBLT, BLT2, and the whole, you have all of it in this.
Hey, Luca, can I control the
Yeah.
Let me see, request control here. So FT code here, and the MATLAB code here. The data is, those are the data. Okay, and the example here, those are just example from
That's Jack's.
Jack's.
I didn't read them.
Hey, I haven't read your reconstruction step. Is that saying like the data is in this folder?
No, it wouldn't say that. I mean, data's in data, right? I don't have a step-by-step for like, oh, here's your white light image. You know, it's all mapped for y'all. It's all mapped the same way y'all mapped it. The reconstruction steps are like what I went over before. So yeah, if you want to go down, all right, go up. If you don't mind, go up. Go up, all the way up. If you don't mind, I want to double check. Oh yeah. So basically, a lot of it I'm kind of just pulling from Jack's as far as making the contour, and a lot of the stuff in the beginning, it's all QBLT stuff.
Well, I just saying like, if I just put a note here, you know, like a note. And that one is just the mouse, like a source, just the QD800 source, right?
No, that's the other one. That's the IR die 800 CW.
Okay.
Lead. Yeah. The excitation is 785 nanometers. And actually, if you want, because you were right, let's just call it, data folder, and that's what you called it. Okay, sorry.
Yeah, so it's called maybe just. I think it's important that you know.
No, it is. You're right. I honestly forgot that example folder was even there. like I said, I gutted all of Jack's stuff, and just I kept mostly everything. Y'all have already done a lot of good work and tested everything, so there's no point in me redoing it.
And do you know the concentration in your on top of your head?
It was 2 milliliters was the total volume. The concentration is going to be whatever the it is for the reconstitute.
Okay, and let me. It's safe, right? I think.
Yeah,
already
it's safe right now.
Yeah. Yeah.
Usually just, okay.
Yeah. The other thing, can you put the? I'm sure you already have a solution. Can you just copy a solution here?
Oh yeah, that's a good idea. Give me 1 second. Let me make sure I'm in the right computer. Okay, do we have both of them up? So one thing I guess I forgot to tell y'all, it's not bad, it's just kind of annoying. So I'm going to go ahead and control copy. And actually I'll show y'all here right now. One of the biggest annoying things, so if you can save all of this, okay? You can save this entire scene. The issue is when you go to open it up again. So you can see here, I've saved this. Granted, it was 2 months ago, but I saved this, and I did what y'all just saw. When I go to open it, it does this, right? So if you go to your model, it's the same reconstruction 4 I showed y'all before. For some reason, I cannot figure out why. It just kind of messes up. Like it's like weird. The threshold changes and kind of like I don't know what it does, but basically what I do is I go over here, I delete it. Right click, delete model, and then you can go back, find your VTK file, drop it in, click OK. You kind of have to do the thing over, and maybe you can talk to. I'm probably doing something wrong.
Yeah, because actually the VTK file you input actually is model, is the 0-1 cases. Just it's not an image. No, sorry, it's a model. Actually, in the NIRFAST, if you use the model, actually they will have the overlap. Once the overlap, since I saw that also. Just once you have an overlap, the later one will cover the previous one, and the coverage will be delayed at the previous one. So I think this is the case at the slicer, not the
Okay, I mean you can talk to Hamid about it. Basically, I just deleted the model and then put it back in.
Yeah, because actually I made this in the I made this previously in the slicer. I'm trying to generate a model, and later I found a model maybe not perfect. I generated the other one. I found the second one can overlap on the first one, and the first one will delay part of the overlap region.
Well, the thing is, I only have one model, though, right? I have one model.
Yeah, if you have one model, it should be fine.
Yeah, but that's what I was showing you. Even with one model, it does this weird thing. And you even saw, here, my threshold is kind of large, but if you saw when I opened it up, it was from 0 to 2. And I guess you could just change that, but yeah, I think that's about it. Any other questions?
Hey, look, if Jack and Danny doesn't have further problem with the near fast reconstruction. Can we go to the Alex stuff?
So I don't remember any of the Alex stuff, to be completely honest with you. I haven't done it in 5 or 6 months.
Okay.
But what I did give in the thing, which I don't mind like sitting down, but it's going to be both of us trying to figure out where everything is. What I did do, you go here, you go here. I put the MP4 file with Alex Close, and this explains everything.
Oh, the video file. Okay.
Yeah, so this is him going through every single, like, okay, this is this, this is that. It goes through everything.
Okay.
And once you know that, it's pretty simple.
I remember, like in the beginning, you have a difficulty to install the software, right?
Yeah, but if you look here, I also put the install. It's called mSYS64.
Okay.
Because he told me to install mSYS, which is different than mSYS2. So I do have that procedure here on how to do that. And then what you need to do, because you do have to change the environment variables. There's a couple of things, but I have it, you know, how to install that mSYS64.
And do you use remember? Do you use like a JAX code to change the from contour to the regular mesh, or you use from near fast, then convert to the regular mesh?
I use JAX code. JAX code is easier to use to convert to regular mesh.
Okay, and then you become like input to the Alex Close code.
And basically you end up, again, I have the MATLAB code. You have the main. Applying the data is very similar. It saves everything. And then I also put a display reconstructed data file as well. And he actually goes over how to run it in the thing as well.
Okay. Can we open just your MATLAB main? Just take a look and see what's inside. The main code, MATLAB code.
Yeah, let's go ahead. Let me double check everything. No, that's not what I want. Yeah, what we may want to do is give me a little bit to go through it. So again, I haven't looked at this in, it's been several months because I did it and then there was no reason to do it because it really was, it didn't seem to work very well. Yeah, it's been a long time doing it and then it didn't really work.
Look, it's okay. I think all we just want to get some idea what's the like which functions to start with. I mean, you can.
Yeah. I'm trying to. Again, give me. It should be written down. Where would it be written down?
Because I remember you told me you have a like a written document.
No, so the written documents just to install. Because to be completely honest with you, I gave up on it. I stopped even looking at it because, as far as I was concerned, it was a waste of time. It was wasting my time. It was wasting a lot of my time. Yeah, I didn't even save the reconstruction of what I got because it was that bad. That doesn't mean that it's wrong. I stopped doing it. You know, I spent probably a week or two doing this and then, oh, hey, look, it doesn't really work. Great. So I just quit messing with it. No, I'm sorry. Shouldn't it? Is this the right code? Yeah, it should have been that. But this is not right. Yeah, let me double check this.
Yeah, because I think the example you show probably the one used by Jack before, because you see you have 4 wavelengths.
No, yeah, that's why I'm kind of confused, is because it shouldn't be like that.
Right.
Look,
it's okay. Why don't you?
It's not okay. Like I said, I worked on it, got nowhere with it, so I stopped. It was a waste of time. And it looks like it's going to waste more of my time.
No, I'm saying like maybe you can spend some time just put the right folder into the transition folder, and next week just let us know which file you want to is the starting file.
Yeah, I mean we can look at it. Like I said. What? Oh, hey, look at that. That is a lot bigger. Yeah, that's weird. Huh. Yeah, here it is. Yeah, basically I just gutted the QBLT again. Yeah, I'm sorry. I don't know why it... Because this is called code algorithm BLT. Yeah, I just gutted that. Okay, let me double check. And I'll make sure it works. I mean, I don't have... Do I have it? Yeah, I have it. Yeah, I'll just double check it. It'll be fine.
Look, I mean, why don't you just check later?
Yeah. I'm just trying to... Where the hell did this come from then? Okay, yeah, that's fine. I'll deal with it later. Any other questions?
I don't have. Jack and Danny.
I don't have any questions.
Yeah, neither I until now.
Okay, so I want to go through actually our next week schedule. Can I?
Yeah. Do you want me to?
Yeah, I'm going to share. Yeah, share screen. Yeah.
Yeah. Hold on. Let me try and get out of this thing.
And let me just stop the recording. Let's go off the meeting first.
Yeah.